the greatest mystery about the universe? One of the things I love about science is that you can ask big questions. How large is the universe? How old is the universe? What is the universe made of? And actually test possible answers to those questions using data. What I'm going to talk about today is what I think is currently the greatest mystery about the nature of the universe. And that is this. That is, he'll put it on, but that is this. If gravity works the way that we think it does, then the motions of gas and stars in galaxies and clusters of galaxies is too fast. There should be more matter to hold it in. Otherwise, it's so fast that it has escape speed. So we hypothesize that there's additional matter holding it in. And we call this dark matter. And it's not just a little bit of dark matter. Current models of the universe suggest that there's 5 times more of this dark matter than regular matter in the universe. And it gets worse. If you observe galaxies on a very large scale, they're apparently getting farther away from each other. The universe is expanding. The problem is that observations suggest that the expansion rate of the universe is increasing with time. This should not happen, because matter attracts other matter. If the universe did start off expanding, it should be slowing down as all the matter attracts all the other matter. So we hypothesize that there's a substance filling the universe that can do this, that can make the expansion rate increase, and we call it dark energy. And there's not just a little bit of dark energy. In current cosmological models, there's 15 times more dark energy than the energy in regular matter. So there's 2 possibilities. Either the universe is filled with mysterious dark matter and even more mysterious dark energy, or gravity is wrong, because that's what we use to come up with their existence. So this is the problem I'm going to focus on in this talk. But first, let's put this debate in context and recognize, see if it works this time, and recognize that this is the 100th year anniversary of an event in astronomy that was called the Great Debate. Although some astronomers would argue that it wasn't that great and it wasn't really a debate, it did draw attention to some crucial points about the universe. So this was something that happened in Washington, D.C. at the Smithsonian Institution, and this is a press release for that event that came out that day approximately 100 years ago. I think this is a pretty exciting title for a press release. How many universes are there? This evening, 2 California astronomers will discuss the size of the universe and present their views on whether or not there's only one or several universes before the National Academy of Sciences, which is now in Washington. So, what was the answer? One universe or several universes? On one side of the debate was Harlow Shapley. He presented evidence that the Milky Way, which is the collection of billions of stars that we reside in, and that at the time was referred to as the universe by many people, was actually much larger than people had measured it to be before. On the other side of the debate was Heber Curtis. You might think since Shapley was arguing that the universe was bigger, that Curtis was going to argue that it wasn't. But no, Curtis was actually arguing that the entire universe is unimaginably larger than even Shapley thought. And here's why. People had long known that there were smudges in the sky called spiral nebulae, but they didn't know for sure what they were. Some people thought maybe they were relatively nearby systems nearby in the Milky Way, like individual solar systems in formation. But Curtis was arguing that these were actually systems with the billions of stars in them themselves, like the Milky Way, but so far away that they just look like a smudge on the sky. This is a huge change in how we would have thought of the universe, that it's a huge, vast, almost empty universe dotted with little island universes, they were called at the time. We would now call them galaxies. The Great Debate of 1920 was resolved within 5 years. The key was recognizing a certain kind of pulsating star in the spiral nebulae that had a known intrinsic brightness. And you could compare how bright you knew it was with how bright it looked to get the distance, because the farther away it is, the fainter it looks. And what was the answer? The answer was indeed that these smudges on the sky were entire systems of billions of galaxies like the Milky Way, but almost unimaginably far away. You could say that the great debate of 1920 was resolved with the discovery of galaxies outside our own. So back to the great debate of 2020, which I argue is whether the universe is filled with dark matter and dark energy, or if gravity is wrong. It would actually be a miracle if our theory of gravity were totally correct. We can only see so much information about the universe. So even if we come up with a theory that describes everything that we know about, later we'll discover more, and that theory won't necessarily be able to explain it. So, for example, take Isaac Newton's theory of gravity. It did a great job, and still does do a great job, of describing how things fall to the ground and how things can orbit the Earth. But in the 20th century, it was discovered that another theory of gravity, a more modern one, Einstein's general relativity, actually does a better job of matching precise measurements. How about general relativity? Well, there are reasons to think that's not the final story either. For one thing, on very small microscopic scales, general relativity is mathematically inconsistent, unfortunately, with another very successful theory from the 20th century, which is quantum mechanics. And I'd also like to point out that there's a reason why we don't know everything going on the very, very large scales either. So we won't be able to match that with the theory of gravity that we come up with. It's a really interesting reason. It appears that the universe is about 14 billion years old. This means by itself that we would not be able to see things that are really, really far away. To see something, we need to see light traveling from that object to us. If something is so far away that even in 14 billion years, the light has not had time to reach us, then we cannot see it. So we can see a lot of universe, but presumably we're in this kind of bubble of what we can see, light having had time to reach us, and we just cannot access what the universe is like on a larger scale. So how can we get at this problem of whether dark matter exists or if gravity is wrong? Well, one approach is to try to detect dark matter. So in like a detector on Earth. You would hope that if we detect that it's there from the motions of stars orbiting around in galaxies, we'd be able to detect it also in other ways. And actually, ideally in ways that don't involve gravity at all. Take the sun. We think we feel confident saying the sun is there because we detect it in a lot of different ways. One of those ways is gravity, the Earth going around the sun, the planets going around the sun. But we also see sunlight. We can also detect charged particles streaming away from the surface of the sun. We detect particles that are called neutrinos that are produced in the nuclear reactions in the core of the sun and come streaming past us. There are many different reasons why we would say that the sun exists. Now, maybe dark matter only interacts through gravity, but even then, you could look for it in a way that's different from looking at how fast things move around in a galaxy. You could set up a detector in a lab that could potentially see it even if it only interacts gravitationally. And there are detectors out there on Earth looking for dark matter. This is something that is happening right now. And there have been some tantalizing possibilities of a discovery, although nothing conclusive yet. There's another direction you could go to study this problem. You could develop a new theory of gravity. Oops, didn't want to go back there yet. We're still here with gravity. We're still here with gravity. We haven't gotten rid of gravity yet. So one of the other things you could do is come up with a new theory of gravity. And what you could do is say, okay, I'm going to see if I can find something that explains everything just as well as our current theory and potentially does not require the existence of dark matter and dark energy. Now, hopefully what you can also do is predict something that you could observe in the future that is different from a prediction using gravity as we know it, so that you could test to see which is better in the future. And people are doing this too. People are working on this as well. And again, there are some tantalizing possibilities, but nothing conclusive yet. So what I'm doing is working with collaborators on yet another approach. We have a project called the Arecibo Pisces-Perseus Supercluster Survey. And what we're doing is we're looking at huge clusters of galaxies, and even larger filaments, where the clusters of galaxies are arranged along the filaments. And what we're checking to see is if we can see galaxies being pulled towards these filaments that are primarily made of dark matter and are predicted to exist in theories. So I'd like to show a simulation that shows a filament forming and evolving. This is from something called the Illustrious Simulation. And so the idea is that regions that are less dense, that material is pulled into the denser regions by gravity, forming a network of filaments with clusters at the nodes where the filaments intersect. The scale here is huge. Each cluster has hundreds of galaxies inside it. So as time goes on, the smaller filaments merge into larger filaments. The small clusters merge into larger clusters. The clusters actually become filled with hot gas. And eventually you even start seeing explosions, what appear to be explosions, caused by the hot material that is spewing from regions just outside supermassive black holes in enormous galaxies. So what I am most interested in right now with these simulations is what do they say about the motions of galaxies towards these filaments? Is it possible for us to say that we, based on theory, because this encapsulates our current theoretical models, that we could say, how do we expect, based on current models, galaxies to be falling towards filaments in a very precise way? So what we have done is we've identified hundreds of filaments in simulations like this, and we've tried to see if, on average, there's a very well-defined pattern for how galaxies are gravitationally attracted towards the filaments. And that is what is shown here. It's just a way of saying there is a very well-defined pattern for how fast galaxies are moving towards filaments based on how far away they are from the filaments. So, what we want to do now is compare this theoretical prediction to actual observations of the universe. So what we want to have is a map of galaxies moving towards a filament. We want to know where the galaxies are and how fast they're moving. How can we do this? It's not trivial to figure out the location of a galaxy. Remember, this was the problem with the discovery of galaxies at all. How do you find out how far away it is? Remember that when we were figuring out that galaxies existed at all, we used a special kind of pulsing star, and we knew how bright it really was, and we could compare that to how bright it looks to figure out how far away it is. Unfortunately, these galaxies that we're looking at are too far away to see that kind of star. But there is another method that's kind of similar, a little more complicated, that we are using. And it's based on an observation that the speed of galaxies and gas in a galaxy going around like this is related to the amount of mass in that galaxy in the form of stars plus the amount of mass in the form of loose gas. And the amount of stars and the amount of loose gas is related to how bright the galaxy intrinsically is. Perhaps not surprising. There's more stuff there. We expect it to be brighter. So again, we can say we know how bright. If we can measure how fast it's rotating around, then we can say we know how bright it naturally is, intrinsically is. Compare that to how bright it looks in the sky, and then we can infer the distance because it's going to look fainter if it's farther away. What about information about the motions of galaxies? We need to know that too, to map out this pattern of falling towards the filament. It would be nice if we could see galaxies like move across the sky as they're attracted to a filament, but they're so far away, it's totally not measurable. But there's a component of the motion that is towards and away from us as well. And it turns out that is something we can measure using something called the Doppler Effect. If something giving off a wave, including light, is coming towards us, we perceive the wave as being bunched up as it comes towards us. If it's going away, it looks to us like a longer wavelength, like it's going away. So you can actually calculate how much something is coming towards you and going away if you can measure this. There's one complication, and that is that as the universe expands, the light, the wavelength of the light, actually stretches with the expansion of the universe. So this also affects the wavelength of the light. But we can understand how much an effect that has if we've already figured out how far away the galaxy is. If it's farther away, then more expansion of the universe has happened to that light as it has traveled towards us. And we can subtract that out, and the rest of the effect on the wavelength is because it's literally moving towards or away from us. So this is how we map it out. And the last thing I'd like to show you is the equipment that we're using to do these measurements. For the information about stars, we're using a huge database called the Sloan Digital Sky Survey, which was made using a telescope at Apache Point Observatory in New Mexico. For the information about the gas, we have to use a very different kind of telescope. If loose gas is hot enough, it visibly glows, but most of the loose gas in these galaxies is not that hot. So it would be invisible to a telescope like this. Luckily, it does give off light in the form of radio wavelengths. So we're using actually the second largest telescope in the world, the Radio Observatory at Arecibo in Puerto Rico. This, for a long time, was the largest telescope dish in the world. But just a couple of years ago, a larger one was built in the southwest of China called FAST. But even the second largest telescope in the world is really, really large. To get a feeling for how large that is, the dish is 305 meters across. There's a dome hanging over it, which is basically a multi-story building that houses detectors. There's a path around the circumference that's about 1 kilometer long, over half a mile. So with this huge dish, we're able to see the loose gas in galaxies that are hundreds of millions of light years away. So what we're in the process of doing is scanning a region of the sky where there's a big filament that goes across perpendicular to our line of sight. And for each of the galaxies, point-like in this map, we are looking at it with that huge Arecibo radio dish and measuring how far away it is and how it is moving gradually in strips across the sky, covering the entire region of the filament, so that we can map out how the galaxies are moving towards it. So this is a work in progress. Some people in the room are working on this as we speak, right, mentally. So the culmination of this is going to be to compare what we came up with from the simulations to what we measure for the actual universe. If they're consistent with each other, then as far as gravity goes, so far so good. Then we can ask more detailed questions like exactly how much dark matter has to be in that filament for there to be a very specific speed of galaxies going towards it. If the simulations and the observations of the real universe are not consistent with each other, then something is wrong with our models. Maybe we need a new theory of gravity, in which case our information about how galaxies are moving towards filaments has to be on the list of things that the new theory can explain. So I want to end with just two brief thoughts. One of them is that it's really important to approach a problem from several different independent perspectives. In this case, there's this weird thing that either gravity is wrong or most of the stuff in the universe is mysterious stuff we haven't detected in any other way. So I think it's a good thing that there are many different ways people are approaching this. Thinking that maybe dark matter is there, maybe we can detect it. Thinking that maybe gravity is wrong, let's try to come up with new theories of gravity. The way we're doing it is we're basically saying, what are all the implications of the current model of gravity? Are any of them inconsistent with observations that we haven't checked yet? But doing all of them is important at the same time. And the very last thing that I want to say is that keep your eyes peeled, because all of these approaches, I think, are kind of on the verge of potentially coming up with interesting answers. In fact, last spring, there was an announcement that maybe one of these dark matter detectors had actually detected something, although other detectors weren't able to back that up, so that's not clear at this point. But remember how suddenly the great debate from 1920 was resolved. Within 5 years, we had the answer. This is summarized in this remark from the astronomer Alan Sandage. What are galaxies? Very few people knew in 1920. All astronomers knew after 1924. So what will we be able to say 5 years from now? What is dark matter? Very few people knew in 2020. All astronomers knew after 2024. Thank you.